Alright, let's get started. This kind of freaked me out a little bit because black hole seems really complicated, but apparently we're just worrying about the outside of the black hole, which is the edges, and that I guess has a, like, when you calculate that, there's like an easier way to kind of quantify it. But honestly, doing this kind of still confused me a lot, so I'm gonna still try my best to explain whatever question it throws at me to help you guys. So first, I'm just going to say what it gives us. It gives us these constants right here and equations. So constant R is this dude's name's radius. I would butcher it if I said it. And this is just to find this right here. We have our Newton's gravitational constant and our speed of light. This is the temperature of the black hole. And this is our Planck's constant. I probably said that wrong as well. And then we have your boy Einstein's E equals mc squared. We all recognize that one. So first it gives us this Q equals mc to the change of T, where Q is the heat that goes into the system, M is the mass of the black hole, C is the heat capacity of the black hole, and T is the change in temperature. And that's what it tells us right here. And it also points out that big C is the heat capacity and little c is the speed of light, and to not get that confused. So it's saying, suppose we throw a rock into the black hole, what's the change in energy? And we can use this equation right here to figure it out. And when the black hole eats the rock, or sucks it in, I guess, the mass turns from m to m plus q equals m plus mc squared. And this small m is, I'm assuming, is probably the mass of the rock. So it's asking what's the corresponding change in temperature and what's the heat capacity. I'll point out this important note at the end. So first, let's do change in temperature. Change in temperature is, we can use this equation right here. We just isolate the T and we get Q over MC. But we can use this equation right here to find our Q. So the first thing we notice is that there's M's on both sides. We cancel those out, and then we get Q is equal to MC squared. So that when we plug that Q into the Q right here, we get MC squared divided by MC. And remember that this is small m, this is big M. Small m is rock mass and big M is black hole mass. So to find our heat capacity now, first thing I'm going to do is I'm going to manipulate this E equals mc squared equation to get m equals E divided by c squared, to plug it into this m to replace it. So since this is in a fraction under it, we multiply what's on the bottom to the top and keep what's at the top to the bottom. So that's why I have the E at the bottom and the c squared to the top. So these c combine, and then we get c5. So the reason why I switched these e's and t's, first of all, you can just multiply one out and then divide it back under. So that's how I got this right here. Is the video I watched tells me that if you take the derivative of, in terms of dE divided by dt of this equation right here, you can get the heat capacity. And I'm gonna put the link to the video in the description because I found it very helpful. And he explained a lot of like the mathematical works of it, and he also goes into how black holes work as well, and I thought that was really interesting because it's honestly a really interesting thing, but also very complicated. So when you take the derivative of this in terms of t, so first keep in mind that everything we're taking in terms of t, so everything else is a constant, so everything else stays the same. As for now, we just take the derivative of 1 over t, and that just leaves us with and -1 multiplied by 1 over t squared. And that's why we have this negative in the front, and our t is now our t squared. So the important note is they wanted to point out is that our heat capacity is negative. The more you add energy to the black hole, the colder it gets. And it points out that this is kind of weird, and the black hole sucks up heat, but gives cold. It gets colder. So as for the next part, we have entropy. So they're just asking us how we get here to here. So I'm going to show you that. So we have this equation right here. I plugged in our temperature, and our temperature is inverse because it's 1 over t. And keep in mind, this is in terms of m. Apparently I made a mistake, and this is not actually just an extra m hanging over. Because we're going to be taking this derivative in terms of m, multiplied by that c squared divided over 1. So this is what we have right here. We can see that there's a c at the top, c at the bottom. We could cancel those out to just get a c. And there should be a dm on this outside part right here because we should be taking the integral of it, like this whole thing. So it should be ds equals this multiplied by dm. And then so we take the integral of the inside and the outside. So we take the integral of the outside, which is 0 to s on the outside, and then we take the integral of the inside. But since we're just trying to take it in terms of m, we can keep everything else as a constant, so that's why I moved it to the outside of the integral. So we're just taking the integral of m. And when you take the integral of m, you get 1/2 times m squared of 0 to m. And then this ds to just become s. So when we multiply everything over, we have s equals 1/2 times m squared multiplied by this whole part, which is the temperature of the black hole. We can see that we can simplify it to make this a 4, and we have m squared at the top, and that just leaves us with s equals 4 pi multiplied by g multiplied by kb divided by that dude's name with the p constant multiplied by the speed of light. And then of course there's this m squared on the outside. And then keep in mind that is a g right here. I know it kind of looks like a 6, but I apologize for my bad handwriting. But yeah, that's how we get here. So there's an extra commentary in here. I thought this was pretty interesting, that you don't need to discuss this in your explainer video, but it might be helpful giving context. That you could write that dude's names of radius in terms of this, and then the p dude's named length estimate is the smallest length scale where known physics makes sense. Then you get this, and then that 4 pi r thing right here is the area of the black hole. What we found here is the entropy of the black hole is proportional to the area of the black hole. This is very surprising. In contrast, for the problem 1, we found that the entropy of an ideal gas scales to the volume of the ideal gas, as if all of the physics of the black hole are encoded on the surface. The idea of the black hole lives on the surface of the black hole rather than the volume it lives in actually led it to one of the most big breakthroughs in the theoretical physics, also known as the holographic principle. And that kind of deals with the idea of kind of like different dimensions. And that's what our Professor Tornado deals with. And I thought that was pretty interesting. So that's all. Hope you have a great